Bismillahirrahmanirrahim. Assalamu alaikum, students. Today, our topic is the idea of polarization. We have already discussed the effect of filling the space between the plates of a charged capacitor with dielectrics. We discussed that the capacitance of a capacitor increases, and we defined the dielectric constant Ke as C over C naught, where C is the capacitance of a capacitor with dielectric between the plates, and C naught is its capacitance when there is air or vacuum between the plates of the capacitor. We want to continue on that. As we already discussed, that matter comes in many varieties. We have solids, we have liquids, we have metals, we have gases, we have glasses. These are different varieties of matter, and these substances do not all respond in the same way to electrostatic fields. Nevertheless, most everyday objects, I should write most everyday objects belong at least in good approximation to one of two large classes. Which classes? One class is conductors, and second is insulators or dielectrics, right? Now, conductors are substances that contain an unlimited supply of charges that are free to move about through the material. In practice, this ordinarily means that many of the electrons are not associated with any particular nucleus, but roam around at will. In dielectrics, by contrast, I should write all charges are attached to specific atoms or molecules, right? And all they can do is move a bit within the atom or molecule. Now, such microscopic displacements are not as dramatic as the wholesale rearrangement of charge in a conductor, but their cumulative effects account for the characteristic behavior of dielectric materials. There are actually two principal mechanisms by which electric fields can distort the charge distribution of a dielectric atom or molecule. One is stretching, and second is rotating, right? We have already discussed the behavior of a neutral atom in an electric field. As we discussed, if we place a neutral atom in an electric field, what happens? Although the atom as a whole is electrically neutral, there is a positively charged core, as we discuss, nucleus, there is a nucleus, right, at the center, and a negatively charged electron cloud surrounding it. So there is a negatively charged electron cloud surrounding it. Negatively charged electron cloud. So when you place it in an electric field E, what will happen? These two regions of charge within the atom are influenced by the field. The nucleus is pushed in the direction of the field, and the electrons the opposite way, right? In principle, if the field is large enough, it can pull the atom apart completely, ionizing it. The substance then becomes a conductor. Now, with less extreme fields, however, an equilibrium is soon established, for if the center of electron cloud does not coincide with the nucleus, these positive and negative charges attract one another, and that holds the atom together. Now, the two opposing forces, the electric field E pulling the electrons and nucleus apart, their mutual attraction drawing them back together, reach a balance, leaving atom polarized, with plus charge shifted slightly one way and minus the other, right? I should write it. The two opposing forces. Which forces? One is the electric field E pulling the electrons and nucleus apart. This is one force. Second is their mutual attraction drawing them back together, back together, reach a balance, leaving the atom polarized with plus charge shifted slightly one way and minus charge the other. The atom now has a tiny dipole moment P, which points in the same direction as the electric field E. Now, typically, this induced dipole moment is approximately proportional to the field. So I can write P is equal to alpha E. Let me name it equation first. So this is the induced dipole moment of the atom, and E is the electric field in which it is placed. Now, this proportionality holds good as long as the electric field E is not too strong, right? Now, the constant of proportionality alpha is called atomic polarizability. Polarizability, right? Its value depends on the detailed structure of the atom in question, right? Now, this was about an atom placing in an electric field. For molecules, the situation is not quite so simple. The situation is not quite so simple because frequently they polarize more readily in some directions than in others. they polarize more readily in some directions than in others. Carbon dioxide, let me show some figure. This shows carbon dioxide molecule. There are carbon atom and there are two oxygen atoms. Now in this carbon dioxide molecule, for instance, has a polarizability of 4.5 into 10 raised power minus 40 coulomb square meter per Newton when we apply the field along the axis of the molecule. If it is alpha, if E is applied along the axis of the molecule, right? But only alpha is 2 into 10 raised power minus 40, and same unit is coulomb square meter per Newton for fields perpendicular to the axis. I repeat, for carbon dioxide molecule, polarizability alpha is 4.5 into 10 raised power minus 40 coulomb square meter per Newton. If the electric field E is applied along the axis of the molecule, but it has alpha of only 2 into 10 raised power minus 40 coulomb square meter per Newton for fields perpendicular to the axis of the molecule. When the field is at some angle to the axis, we resolve it into parallel and perpendicular components and multiply each by the pertinent polarizability. We write it when the field is at some angle to the axis of the molecule, we write its dipole moment as alpha perpendicular E perpendicular plus alpha parallel E parallel, right? In this case, the induced dipole moment may not even be in the same direction as E. I should write it. In this case, this is important. The induced dipole moment may not even be in the same direction as the electric field E. Remember, equation 1, for simple situations like a neutral atom, induced dipole moment is similarly directed as the electric field. But in more complicated situations, that is not the case. As molecules go, carbon dioxide is relatively simple since the atoms at least arrange themselves in a straight line. For a completely asymmetrical molecule, equation 1 is replaced by the most general linear relation between E and P as, let me name this as equation 2. This is my equation 1. Let me write it. For a completely asymmetrical molecule, equation 1 is replaced by the most general linear relation between electric field E and induced dipole moment P, as we write Px is alpha xx Ex plus alpha xy Ey plus alpha xz Ez. Ey is written as alpha yx Ex plus alpha yy Ey plus alpha yz Ez. P z is written as alpha zx Ex plus alpha zy Ey plus alpha zz Ez. Let me name this as equation 3. This was our second one. So first, this our third. Let me check it. Px is alpha xx ex plus alpha xy ey plus alpha xz ez. Ey is alpha y x ex plus alpha yy ey plus alpha yz ez. Dz is alpha zx ex plus alpha zy ey plus alpha zz ez. Px, Py, Pz are the rectangular components of the induced dipole moment P, and Ex, Ey, Ez are the rectangular components of the applied electric field E. Now the set of 9 constants, these are 3, these 3, and these 3. There are 9 constants. We write them in general as alpha ij. These 9 constants constitute the polarizability tensor for the molecule. Their values depend on the orientation of the axis we use, right? And though it is always possible to choose principal axis such that all the off-diagonal terms vanish, leaving just 3 non-zero polarizabilities: alpha xx, alpha yy, and alpha zz. This was about the atomic polarizability. Now, first, let me do a sample problem. We'll do it together. Let me write. Problem goes like this. It says a primitive model for an atom consists of a point nucleus plus Q surrounded by a uniformly charged spherical cloud minus Q of radius A. Figure 1. Calculate the atomic polarizability of such an atom. Let me draw the figure. This is our atom with point nucleus of charge plus Q at the center, and this is surrounded by uniformly charged spherical cloud with charge minus Q. A is the radius of the atom. This is figure 1. Let me repeat the question. A primitive model for an atom consists of a point nucleus plus Q surrounded by a uniformly charged spherical cloud minus Q of radius A, as shown in figure 1. Calculate the atomic polarizability of such an atom. This is the figure 1. Let us move to the solution. This is easy. We know in the presence of an electric field, the nucleus will be shifted slightly to the right and the electron cloud to the left, as shown in figure 2. Let me show the figure 2. Now, nucleus will be somewhere here, plus Q. This is electron cloud with charge minus Q. This is electric field. We know the relation force on a charge in an electric field is given by QE. So positive charge will experience force in the direction of the field, and negative charge will experience the force opposite to that of the field. So nucleus is shifted to the right and electron cloud to the left. So there is a separation distance between the center of negative and center of positive charge. We denote it by D, right? This is our figure 2. Now, because the actual displacements involved are extremely small, it is reasonable to assume that the electron cloud retains its spherical shape. Let me write it. Because the actual displacements involved are extremely small, it is reasonable to assume that the electron cloud retains its spherical shape, right? Now, let us assume that equilibrium occurs when the nucleus is displaced at distance d from the center of the sphere, as shown in the figure 2. At that point, the external field pushing the nucleus to the right exactly balances the internal field pulling it to the left. Write it at equilibrium. This figure shows the equilibrium situation. The nucleus is displaced a distance d from the center of the sphere. Now, at equilibrium, the external field pushing the nucleus to the right exactly balances the internal field pulling it to the left. E is equal to EE, where E subscript E is the field produced by the electron cloud. Now, the field at a distance d from the center of a uniformly charged sphere is EE is equal to 1 by 4 pi epsilon naught QD by A cube, right? 1 by 4 pi epsilon naught QD by A cube. At equilibrium, then E, the external field, is therefore equal to 1 by 4 pi epsilon naught KD by AQ. Now, or P, which is QD, electric dipole moment, induced electric dipole moment, is 4 pi epsilon naught AQ times E. 4 pi epsilon naught AQ times E. So when we compare it with P is alpha E, we get alpha is 4 pi epsilon naught AQ, which can be written as 3 times epsilon naught into V. Let me encircle it, where V is the volume of the atom, which is 4 by 3 pi AQ is the radius. So if you put here alpha is 3 epsilon naught 4 by 3 pi AQ, is 3 will go and get back your result epsilon naught 4 pi AQ, right? So this is our answer for the atomic polarizability. So for this primitive model of an atom, atomic polarizability alpha is 4 pi epsilon naught AQ, which is equal 3 epsilon naught V, where V is the volume of the atom. This is all for today. Don't waste your time. Go through all the video lectures and don't forget to subscribe and like my channel. Thank you. God bless you. Assalamu alaikum.